In chapter 4, there's actually only one single section, which is why it's just section 4, no decimal included. Uh, and because of that, it might be a little lengthy, but might pretty. It's expected that we go pretty fast through it because of the fact that we already know a lot about polynomials from previous classes, even from high school, middle school. So we'll just go into some depth into not even that much depth, but we'll go over some things that we do need to know for this class. So first things first, we're going to define the real part of z and imaginary part of z. So here z is a complex number, z equals a plus bi, where a and b are real numbers. So the real part of z, we denote rez, as in real part of z. And the imaginary part as imz. Right, so a here is rez, the real part of z, and the b over here is the imaginary part of z. So for every complex number, we have z is equal to raz, or real part of z, plus the imaginary part of zi. Next definition, we have the complex conjugate. So the complex conjugate, we just put a little bar over it, over the number, and we define it by, instead of having addition, we have subtraction here, but everything else remains the same. Now the absolute value of a complex number is defined to be the square root of the real part of z squared plus the imaginary part of z squared. That is how we're defining the absolute value of a complex number. So a little simple example practicing these definitions. If we have the complex number 3 plus 2i, then the real part of z is 3, and the imaginary part is 2. The conjugate would be 3 minus 2i. And finally, the absolute value would be 3 squared plus 2 squared, and then taking the square root of that, which is the square root of 13. So that would be the absolute value of this complex number z. And in fact, you could verify yourself that z is equal to the conjugate if and only if z is a real number. You can verify that, but we're going to go over some properties that might include this. I think so. Although we won't even prove them because of the fact that this lesson is long and they're quite simple. They're good exercises. You can do them by yourself. So here's a theorem. Suppose w and z are complex numbers, then z plus its conjugate is equal to 2 times the real part of z. Z minus its conjugate is equal to 2 times the imaginary part of z, I. And again, you can verify these simple calculations. Just use the definition. The product of z and its conjugate is equal to the absolute value of z squared. The conjugate of the sum of w plus z is equal to the sum of the conjugates of w and z. And same thing with their product. The conjugate of the product is equal to the product of the conjugates. Another thing, the conjugate of the conjugate of z is equal to z. Another part, the absolute value of the real part of z is less than or equal to the absolute value of z. Same thing with the imaginary part of z. The absolute value of the conjugate is exactly the absolute value of the z. The absolute value of the product of complex numbers is equal to the product of the absolute values. So as you can see here, I'm getting mixed up with the words there. And finally, this one is a really famous one. we use a lot known as the triangle inequality. And the triangle inequality tells us that the absolute value of the sum of w plus z is less than or equal to the absolute value of w plus the absolute value of z. And in fact, these are easy to verify. The only one we're going to prove is the last one because that one's really so important and we use it a lot. So proof of the triangle inequality. So first off, we have that w plus z, the absolute value squared, is equal to w plus z times w, the conjugate of w plus the conjugate of z. Now, why is this the case? Well, we're using this property here, right? This third one. This is z. This is the conjugate of z. And that's equal to the absolute value squared. Now, shouldn't this be a whole line if we're doing the conjugate? Well, yes, but then we can use this other property here. Right? This fourth property. Now we can use this property here. Right? They're equal. So it doesn't matter if we have those two separate lines or one big line. They're the same thing. They're equal. Again, you should probably verify as a good exercise. So anyway, we have this equality. Well, that's just equal. Just doing some algebra, distributive property. And then we get that that's equal to the absolute value of w squared plus the absolute value of z squared. We have this and this. Again, just using those properties from the side, we're getting this equality. Nothing too bad. But now we have that this is less than. So how do we know that this new expression is greater than or equal to this expression at the top? Well, let's see. These two are the same. These two are the same. So we're claiming that this here is greater than or equal to this sum. Right? Now, how do we know this? Well, this here is equal to, let me erase the red. This here is equal to 2 times the real part of w z conjugate. That's what that's equal to. Right? And this is what we know to be less than, okay, so real we know that this is less than or equal to this by this property over here, right? That is how we're getting this. So again, this I'm circling in red is equal to this over here. And we know that the 2 times the real part of w times z conjugate is less than this here. That's how we're getting this inequality. So I'm going to erase this just so it doesn't distract us. That is, oh, actually I put it out of order. There it is. So again, this here was equal to this part, which is less than this part. Again, just using our properties, which is equal to, now we're just using our properties. And finally, we get that this is equal to w, the absolute value of w plus absolute value of z squared. And now we can just take the square root of both sides and it gives us our theorem. Our theorem holds our triangle inequality. So that's nice. Very important property. So now we'll be moving on. A polynomial. So recall that a function p from f to f is called a polynomial. If there exists scalars a0 to am in f, such that we can write a polynomial in this form, where z is our variable here, for all z in f. The zero polynomial we define to have degree negative infinity. And there's a reason for that. Which I'll go over shortly. Hopefully I won't forget. But first, let's go over this theorem. Suppose we have the polynomial equal to 0. Well, then that means that all scalars must be equal to 0 for this to be true. How do we prove that? Well, if not all the coefficients are 0, then we can change m, or we can assume that am isn't equal to 0. So then we're going to put z equal to this polynomial here, or sorry, not polynomial, this rational expression plus 1. So z is definitely greater than or equal to 1 because, well, here we have a fraction that's greater than 0 plus 1. It could be less than or equal to 0, sorry, that fraction, and plus 1, so we know z is greater than or equal to 1. So z to the j must be less than z to the m minus 1, right? Because j must be less than m minus 1, so that's why this inequality is true. Now we can use a triangle inequality. We have this polynomial here. We're using a triangle inequality to get this here now. And what do we know that is less than? Well, that's less than the absolute value of a sub m times z to the power of m. Here, this may not be so immediately obvious. You can do some simple algebra. It shouldn't take you too long. Make sure to use the definition, kind of see what's going on, play around with it. But we're just using simple algebra to give us that inequality. So therefore, this polynomial is not equal to this polynomial. Right? It's not equal to the negative part of it because we have the inequalities. There are no equalities. So that's why it can't be equal to the negative part of it. It would have only maybe been true if this was equal, but not less than. So because of that, it can't equal negative am z to the m. So we can conclude that our polynomial indeed does not equal 0 by just sending this part over to the other side and equaling it to 0. Therefore, we get our theorem here. So if it wasn't obvious, or if it wasn't apparent, we use the proof by contrapositive here. And so this result implies that the coefficients of a polynomial are uniquely determined, right? Because if a polynomial had two different sets of coefficients, then subtracting the two representations of the polynomial would give a contradiction, right? Like to the result of this result we just got. So now coming back to the degree of 0, this is just because if we have degree of two polynomials, so if we were to take the product of two polynomials, their degree is the degree of each polynomial added together. So of polynomials P and Q, we take their degree and we add them. That's the degree of their product. This wouldn't be true unless we set the 0 polynomial to have degree of negative infinity. That's why we do this. So that's why the 0 polynomial is defined to be degree negative infinity. Okay, you may, if you theory course, you may have seen the division algorithm. In this case, we're going to do the same thing, but with polynomials. And you might have even done this since high school. So suppose that P and S are polynomials with S not equal to 0, so a non-zero polynomial. And there exists a unique polynomial Q and R such that P is equal to SQ plus R, and the degree of R is less than the degree of S. So you may want to pause here, make sure you see what's going on. I've included some pictures, let me bring them up. Those are all polynomials. Or this is another way of looking at it. If you remember long division, so here in this case, P would be the blue one. This would be P. This would be S. This would be Q. And this would be R. Right, this is how we should look at it. So P, this polynomial, 2x squared plus 7x plus 7 is equal to x plus 2 times 2x plus 3 plus 1. And what does that show us? Well, just as above, as we see above, this is P is equal to SQ plus R. That's what that theorem's saying. That those polynomials Q and R always exist. And in fact, they are unique. So to prove this, oh, here's another example of long division. So they show us in high school, but here we're going to prove a theorem. So let n be the degree of P and m be the degree of S. Now there's two cases here. And in fact, this can be proven without linear algebra, but this is a linear algebra course, so let's prove it with linear algebra. Well, if P, if the degree of P is less than the degree of S, well then just take Q equal to 0 and R equal to P to get the desired result. Right, so for example, if I had x squared plus 1 is equal to, let's say, let S be x cubed plus 2. So now, what do we plug in for Q and R? What polynomials? Where this is simple, just let Q be 0, so we get that this is 0. And so just set R equal to P, which is equal to x squared plus 1, and we get our equality, we get our result. So that case isn't interesting. That's what that case is saying. If n is less than m, we just set R equal to P and Q equal to 0, and we're done. So let's look at the more interesting part. We can assume now that n is greater than or equal to m. Well, we're going to define a linear transformation, T, such that we have the product of these two polynomial vector spaces. And again, this here, n minus m, denotes the largest degree of the polynomials in that vector space. Similarly with m minus 1. And it maps to P sub n of f, that polynomial. And this is how we do it. T of QR is equal to SQ plus R. So if Q and R are in the null space, well then they must equal 0, right? The polynomials, this here must equal 0, which implies that Q and R must be 0. Right, so this maps, if this maps to the null space, this is equal to 0, which implies that Q and R are equal to 0. Therefore, the dimension of the null space is 0. So we got that out of the way. Now, the dimension of n minus m, the cross product of n minus m, those polynomials, with the polynomials of m minus 1 degree, of at most that degree, is equal to this. So why n minus 1? And then remember with polynomials, if you are in P3 of f, those polynomials most degree of degree at most 3. Remember our basis was 1, x squared, x cubed. And there are 4 vectors in the basis. So that's why this is dimension 4. So that's why we always add plus 1. Right, so here, that's why we have n minus m and then the plus 1. Same thing over here, m minus 1 plus 1, which, I mean, we just subtract, add whatever we need to do, we get n plus 1. So we can use a fundamental theorem of linear maps to tell us that the dimension of the range of T is n plus 1, which is exactly equal to the dimension of P of n, right? We always add plus 1, as I just explained with the example. Therefore, the range is P sub n of f, and hence there exists Q in this space. We take a polynomial Q from that space and a polynomial R from this space, such that our linear transformation holds and our proof is done. That's a quite neat results. The other proof is probably easier, not using linear algebra, but this one's an interesting one as well. And well, we use things that we've been going over, so that's neat. Now we can talk about something I know you are definitely familiar with as well. We're going to be talking about zeros of polynomials. So a number lambda is called a zero or a root, maybe you've heard of a root before, of a polynomial if when we plug in that number we get 0 for the polynomial. A polynomial S is called a factor of P if there exists a polynomial Q such that P is equal to S times Q. Now this here, I'm sure you're familiar with. It just may sound more complicated than it actually is. So like I said before, if it does help you, go ahead and pause and make sure you understand what the definition is even saying. I'll come up with, I'll present an example to show you what the definitions are actually saying. So lambda, which is 2, is a zero of the polynomial 3z squared minus 2z minus 8. Because plug in 2 to the z, and you'll get that it's equal to 0. So that is an example of a zero or a root. And s equal to z minus 2 is a factor of the polynomial 3z squared minus 2z minus 8, because we can get two factors, right? This is q, this is s. So p is equal to qs, or its definition said sq. So that's all that's saying, the factor, right? Remember, your teacher would tell you, oh, just factor it, right? Factor this polynomial. That's all you would do. Those are factors of polynomials. Now, we present a theorem. This is a quite important theorem because it's going to help us with the next theorems. So, suppose P is a polynomial, lambda is a number, then the polynomial, P of lambda is equal to 0 if and only if there is a polynomial Q such that P, the polynomial P, is equal to z minus lambda times Q of z, times that polynomial. So what is that saying? Lambda is a root if and only if we can get a polynomial Q such that if we multiply it by z times lambda, we get our polynomial P. Now, how does this proof go? Well, as you can see, it's not too long. Well, it is an if and only if proof, a biconditional, so we will have to prove both directions. So first, this first direction is quite easy. It's pretty obvious, right? So suppose there's a polynomial Q in P of F such that this is true. Well, then what happens if we plug in lambda for z? Well, this is going to be lambda minus lambda, right? So we're going to get P of lambda is equal to lambda minus lambda, which is just 0, times Q, which is 0, and we get one direction. Not the bend. We just proved one direction of the theorem. Now the other one is a bit more interesting. Suppose P of lambda is equal to 0. Well, then the polynomial z minus lambda has degree 1, right? Because it's a variable minus a constant. That's obviously degree 1. Z only has degree 1. Well, because a polynomial with degree less than 1 is a constant function, The division algorithm for polynomials that we went over last slide implies that there's a polynomial q and a number r such that we get this, right? We went over the proof of why that's true on the last slide. So we can always find a q and an r such that we get p. Well, the equation above, this equation, the one I underlined in purple, and the equation p lambda equals 0 imply that r is equal to 0, right? So why is that the case? Well, because if we plug in lambda for z, this becomes 0, this becomes 0, but this has to be 0, right, for it to be equal to 0. If it's 3 or anything else, then it contradicts our equality. That's how we know r is equal to 0, and therefore p of z is equal to z minus lambda times a polynomial qz for every z and f. One last theorem for this slide. Suppose p is a polynomial with degree m greater than or equal to 0, then p has at most m distinct zeros in f. And we're going to do this by induction. So this is quite neat. So like a quadratic equation has at most 2 zeros, cubic at most 3, so on and so forth. So if m is equal to 0, well then we have a constant function that has no zeros, so p has no zeros. So we're done with that, the base case. Now, if m is equal to 1, wait, that wasn't even the base case. This is the base case. Sorry about that. If m is equal to 1, then p of z is a linear function, and we can find a 0, which is this here, negative a naught over a1. Now we can do our inductive step. Suppose m is greater than 1. We use induction on m, assuming that every polynomial with degree m minus 1 has at most m minus 1 distinct zeros. Well, if p has no zeros in f, then we're done, right? Because it's less than m minus 1, so we're done. It has at most m minus 1. So now, if p has a 0 at lambda, then there's a polynomial, just as the theorem above states, polynomial q such that this equality holds. Well, the degree of q is m minus 1, right? Because p has degree m. And this here has degree 1. So m is equal to 1 plus what? Or, oh, okay, sorry about that. No. This has degree m minus 1. We're saying this is equal to 1. And then times what? Well, m minus 1. Okay, so the equation above shows that if p of z is equal to 0, well then either z has to equal lambda or q of z has to be the 0 polynomial, right? To make the equality true. This is 0, then this either has to be equal to 0 times qz, or z minus lambda times 0. So by our induction hypothesis then, q has at most m minus 1 distinct zeros in f. Therefore, p has at most m distinct zeros in f. And we're done. Okay, now I mentioned here the fundamental theorem of algebra. Every non-constant polynomial with complex coefficients has a 0. This isn't necessarily true for just real numbers. We do have to have work with complex numbers. The proof we go over, so this theorem actually has never been proven or proved using only algebra. The proofs always use analysis. And in fact, I think I first went over this theorem in complex analysis, and it's an easy way to prove it, but you need to know what analytic functions are and how they work. So because of all that, I will not be proving that here, but we do need to mention it because of the fact that it's so important, and we're going to be using it. So if polynomial p with complex coefficients is a non-constant polynomial, then p has a unique factorization, except for the order. We can switch the order around of the factors of this form. So that's quite interesting. So we're going to go over this theorem. Let p be a polynomial with complex coefficients, and let m be the degree of the polynomial. So we're going to use induction on m again. So first, m is equal to 1. Well, then we get a simple degree z minus lambda 1, and a desired factorization exists, and well, it's unique. So now we're going to go bigger than 1. So suppose m is greater than or equal to, just greater than 1, and that the desired factorization exists and is unique for all polynomials of degree m minus 1. So we're going to first show that the desired factorization does exist. Well, as I said, we're going to use this theorem. By the fundamental theorem of algebra, p has a 0. And by the previous theorem from I don't know if it was the last slide or the one before that, we know that there's a polynomial q such that polynomial p is equal to the product of those two, of this factor here and polynomial q, right? Well, because the degree of q is equal to m minus 1, our induction hypothesis implies that q has a desired factorization. And when we plug it in, we're going to multiply it with this one. And it gives our desired factorization of p. Right? So here we're assuming that the desired factorization exists for all polynomials of degree m minus 1. What is that saying? That the desired degree for q of z exists. Well, if we just factor that out, then we have this factor and all these other factors of qz, which then gives us our desired factorization of p. So now the question remains, would this be unique? Well, the answer is yes. Well, c is uniquely determined as a coefficient of z to the m. I mean, that's just how a coefficient is. A number can't equal two numbers. So we need to only show that except for the order, there's one way to choose all the lambdas. So then we're going to take the same thing, but now instead of using lambda, we're using tau. Z minus tau sub 1 all the way to z minus tau sub m for all z in the complex numbers. Well, this side here equals 0 if z is equal to lambda 1, right? Because then this would be 0 multiplied by all the factors, still 0. So this would mean that one of the taus has to equal lambda 1. So if we just relabel them, whichever one it was, we relabel it as tau 1, tau sub 1, equal to lambda 1, and we can just keep doing this. Right, so we can divide both sides of the equation by z minus lambda 1, getting again an equality. And the above equation holds for all z complex numbers, because otherwise, as it says here, by subtracting the right side from the left side, we would get a non-zero polynomial that has infinitely many zeros. So it implies that except for the order, the lambdas and the taus are indeed the same, which proves our uniqueness now. So quite interesting theorem, a long one, not too difficult as long as we understand the previous theorems. And we're good. Now we can do this with real numbers too, but it gets a bit more complicated with real numbers. So we're going to present a few preliminary things we need to know. So first thing, fundamental theorem of algebra fails for real numbers, as I have said. And an example is 1 plus x squared has no real zeros, right? In high school, you may have learned that the roots for that is I and negative I. As you can see here, it never crosses the x-axis, so it has no real roots, although it does have a complex roots, as a fundamental theorem of algebra tells us. So suppose P is a polynomial with complex coefficients. Oh, sorry, is a polynomial with real coefficients. Well, if lambda is in C, if lambda being a complex number is a zero of P, then the conjugate of lambda is also a zero of P. And this proof is actually as simple as it gets, really. We're just using our properties that we learned from the first slide. So we let P be a polynomial, where A naught to AM are real numbers. We'll set it equal to 0, right? Because lambda is a 0. So by plugging in lambda, this should equal 0. Well, what did we learn from the first slide? That a number, if it's real, then its conjugate is the same thing. Therefore, take the complex conjugate of both sides of the equation, and we obtain the same thing, but now with lambda conjugate, the conjugate of lambda. Again, because lambda was was real. Actually, I should say lambda was complex, but we used our properties from the first slide, which gives us that the conjugate of lambda also works as a 0. This theorem, I'm not really going to prove it. It just requires you knowing how to complete a square. But it basically tells us that any quadratic expression, form x squared plus bx plus c, can be factored into two separate factors, x minus lambda 1, x minus lambda 2, where the lambdas are real. And if and only if b squared is greater than or equal to 4c, in other words, b squared minus 4c is greater than or equal to 0. As we know, that's a discriminant that has to be greater than or equal to 0 for us to get real numbers. But we will have to know this for our next theorem, and our final theorem actually. So here's the quadratic formula. We can relate this theorem with the quadratic formula if you want to pause, see the similarities. If you want to look at the proof, it is in Sheldon Axler's linear algebra done right. But like I said, I'm not including it. But now we can go over our last theorem. It's a lengthy one. Suppose P is a polynomial, a non-constant polynomial, then P has a unique factorization of this form now. Now here, notice how there's quadratic expressions as well as the ones we had before. And all these coefficients and lambdas are real numbers. Okay. Well, first of all, if all complex zeros of P are real, then we're done, right? And why is that? Well, because we just use the it would pretty much just be the theorem for the factorization of the complex numbers, right? The one we went over for the complex numbers, the other lengthy one. It'd just be that. So again, if all the zeros are real, then we're done. So now we're going to suppose that P has a zero that's a complex number and not a real number. So by our previous theorem, the conjugate of lambda is also a zero. So that's where we get that we can multiply x minus lambda, x minus conjugate of lambda. And again, we always have that q of x. That multiplied gives us p of x. And this here, if you may want to verify just using some simple algebra, you can get that it's equal to this underlined part. And again, for polynomial q with degree 2 less than the degree of p, because we will be multiplying by a quadratic function. So if we can prove that q has real coefficients, then by using induction on the degree of p, we can conclude that x minus lambda appears in the factorization exactly as many times as x minus lambda, the conjugate of lambda. And that should be, I mean, I shouldn't say obvious, it's not a helpful word, but it should be clear. So to prove that q has real coefficients, we're going to solve the equation above. So we simply divide p of x by the quadratic expression we had. Well, then we get that q is real for all x in R. Right? We're using nothing but real numbers. Real numbers there. This is real number. Absolute value will give us a real number. So writing the polynomial q as this polynomial, again, degree n minus 2 because it's 2 less than p. We can get that 0 is equal to the imaginary part of q of x, right? Because it was real. So the imaginary part is 0, which is why we can just rewrite the polynomial as we would any other polynomial. But with the imaginary, a0, a sub 1 for all x in R. And what does that tell us? Well, simply that all those coefficients, if this is equal to 0, all those coefficients have to equal what? Have to equal 0. Therefore, all coefficients of q are real as we desired. Right? That's what we're looking for. Therefore, the desired factorization exists. So now we turn to the question of uniqueness, right? Of our factorization. Well, remember that this could be uniquely written as this over here. And two different factorization of p would lead us to, well, two different quadratic expressions, which would contradict if this product were to give us two different polynomials, two different quadratic expressions, that would contradict the theorem from the last slide. So we know we can conclude that indeed it is unique, and we are done. So I went over a bit. Sorry, I can't even speak. I went over this lecture a bit quickly because it was lengthy. I don't want you to have to sit here for too long. But if it does help, try to produce the theorems yourself, try to practice them, see what's going on. If it helps, pause videos between steps to try to see what step comes next. But this concludes our section of polynomials, and next we'll be looking at chapter 5, which is having to deal with invariant spaces, eigenvalues, and eigenvectors.